Good morning, everybody. Thank you for coming to the session. I saw our competitors there, what generative AI and football fields and other things. So I appreciate you coming to this session. Um, Looks like we got about 40 people here, so that's great. Feel free to jump right in and ask questions as they arise. I'll see if I can pay attention. I'm pretty monofocal, so hopefully I can pay attention and answer your questions as they arise. So what are we going to talk about today here? We're going to talk about a little bit of history of computer science. Uh, that topic is too big to cover in 35 minutes. So what I've done is pick my favorite parts of the history of computer science, and that's what I'm sharing with you. So hopefully you enjoy it. Let me warn you that my record is 6 students asleep in class at the same time. So we'll see how we do today. And here we go. I should probably introduce myself. John Sorensen. I'm a professor of computer science and software engineering at Butler University. I've been here for a very long time. This is my 34th year. And so let's dive right in. Okay. All right. So we should probably start with a definition of what computer science is. And basically, computer science is the study of algorithms. So what is an algorithm? Well, an algorithm is a list of steps that solves a problem. And an algorithm can solve any kind of problem, and the steps don't necessarily have to be computer steps. So I've got some pictures of baking cookies here. Definitely a recipe is an example of an algorithm, and you can think of the ingredients as the data. So, steps, you solve it. And then what's the equivalent of the computer? Well, that would be the baker or the chef. That's the equivalent. And then what's a program? Well, program is just when you take the algorithm and write it formally in a programming language. Then it becomes a program. But an algorithm, in some sense, it exists independent of any particular programming language. The way you bake cookies doesn't depend on how you write it down. But if you want to communicate that to other people, you need to write it down. So then what is computer science? It's the study of algorithms and their applications. And really the goal, of course, is to see if you can automate things, because we're all lazy and we want to figure out ways to get other things to do our work for us. So that's the goal. All right. So that's computer science. And I need to click. There we go. So what are different parts of computer science? I like to think of it in terms of levels. So we have the bottom level, which is the computer hardware. Computer hardware is there to run algorithms automatically for us so that we don't have to do it ourselves. And I've got a picture here of an Atari 800. That was my first computer in high school. And it had one of those modems that it had the suction cups, and you could put the phone in the suction cups and you would dial up, and it connected to a television for the screen. And this was before computers all had mice. That was a long time ago, but it was fun. An operating system is a program that runs on the computer that makes it easier to use. Basically, it's a program that runs other programs. So that's the purpose of an operating system. And operating systems, especially today, they're complicated pieces of software, and there's all sorts of cool features in them. And so it's a major area of computer science is research and the study of different types of operating systems, creating new ones for different types of hardware. It's an interesting area of computer science. And then the next level up is, well, we have algorithms we want to run on the computer. We have to write them down as programs. What are programming languages all about? How do you design new ones? How do you decide what are good languages? What are bad languages? What's involved in the process of taking a program and converting it into the machine code that the CPU understands? That's all part of programming language research. Then the next level is, how do we build the algorithms that we're going to run on the computer? So the design and analysis of algorithms and data structures is a major area of computer science. And then finally, you can go meta. It's like, what kinds of problems are even solvable on a computer? Are there problems that cannot be solved with an algorithm? And the answer is yes, there are. And in fact, there are infinitely many. So, this is an interesting area. And then questions like, what does it mean for a problem to be hard? And can you quantify that? So these are sort of the levels of computer science in my view. There are other areas of computer science as well, like software engineering, database systems, and artificial intelligence. And at least from my perspective, I think of those as fitting into these other areas in different ways. But these are all major areas of computer science. So I have my Atari 800 from back in the 70s, which was when I was in high school, and then some of the machines that were around back then with the tape drives. You can see that picture down below. All right. How are we doing? Anybody fall asleep yet? Yeah, my record is 6 at the same time, but the percentage of a class, it's 100%. Are algorithms built with binary numbers? Normally, binary is not fun to work with. So normally you don't build the algorithm in binary. Binary is where it ends up after you write it down as a program in a programming language, and then you run it through a compiler. Then what it produces is the binary code that the machine understands, because the computer has to run the algorithm in a program that it understands, as opposed to what a human understands. And so we have to translate between the way people think and the way a CPU thinks. So that's where the binary comes up. And the binary is just, you have wires carrying electricity and high and low voltage. And we normally, like, high voltage just means that's a 1 and low voltage means it's a 0. So we just represent information that way because it has to be done with electricity. So that's the idea. All right, so when does computer science start? Well, we can go back to ancient Egypt. Euclid is an example of, you've probably heard of Euclid, maybe in a geometry class or something like that. But Euclid lived around 300 BCE, and he lived in Alexandria, Egypt. And one of the things, he did many things as a mathematician, but one of the things he did is he wrote down an algorithm to compute greatest common divisors. So a greatest common divisor is just the largest number that evenly divides two other numbers. And on the slide here, I've given some examples of this mod operator, which is a basic step in the Euclidean algorithm, basically taking the remainder from division. So when you learn to do integer division, you have the divisor, and then you construct the quotient, and you have a remainder left over. And this mod gives you the remainder. So for example, I think I have 10 mod 3 is 1. Well, if you divide 3 into 10, it goes in 3 times. 3 times 3 is 9. 10 minus 9 is 1. You have a remainder of 1. And so 10 mod 3 is 1, the remainder. So this is what you use. And in green here, you can see the steps of Euclid's algorithm. So it basically has a simple loop, and you do this mod operator. And when you're done, the answer is computed for you. And so I get excited about greatest common divisor algorithms. I know that's not everybody's thing, but I got to choose what's in the talk. So here we are. Now, one of the other things I like is dinosaurs, and I don't think I worked dinosaurs into the talk at all, but we've got Euclid here. So here's an example. So if I'm computing the greatest common divisor of 15 and 6, we put x is 15 and y is 6, and then we take the remainder from the division. 6 goes into 15 twice, giving you 12, and that gives you a remainder of 3, 15 minus 12. So then that's what r is. And then we just slide the numbers over. So now we have x being 6 and y being 3. And then we do 6 mod 3. Well, 3 goes into 6 evenly, so the remainder is 0. And then when we slide over, y is 0. And then if you look back at the algorithm, that's when we stop, right? Well, x and y are both non-zero there. So, and we just add them together there. 3 is the answer. So that's the way Euclid's algorithm works. And it's kind of cool because you don't have to actually find all the factors of x and y to compute its greatest common divisor, which makes it efficient. So, yep. So it's a good algorithm. I have more pictures of cookies. I like cookie. Maybe you like cookies as well. So we'll have pictures of cookies in the whole talk. Does that help keep you awake? I don't know, but you can think about lunch and do that. All right, so where are we going next after Euclid? Well, we're going to stay with ancient Egypt here, and we'll talk about Eratosthenes. So Eratosthenes was also in Alexandria, Egypt. He also did other things in addition to writing an algorithm. He used to work at the Library of Alexandria before it burned down, and he's also well known as measuring the circumference of the Earth. This is one of the things he did. If I recall correctly, he like dug a hole and like had a stick and measured the angle of the shadow and like timed when the sun was directly overhead. And then he did this in other places and did some geometry and was able to get an estimate. And if I recall correctly, his estimate was accurate within like just a couple percentage points. So it was quite good. Pretty impressive for the time. But we're talking about him here because he came up with this algorithm that we now call the sieve of Eratosthenes, and it's used to find prime numbers. And we like Euclid's algorithm is still used today, and so is the sieve of Eratosthenes. So these are algorithms that were written down around 300, 200 BCE, and we're still using these algorithms today. Wouldn't surprise me if both of those algorithms are present in software on your cell phone. So that's the deal. So the sieve of Eratosthenes is for finding prime numbers. And you might recall that a prime number is any number that's divisible only by itself and 1. And we don't consider 1 to be prime. So the first 10 prime numbers, I've listed them there for you. And how does the algorithm work? Well, I'm going to show you an animated GIF that I took from Wikipedia that illustrates the algorithm. And there we go. So basically you start with 2 and then you cross off all multiples of 2. That's what the red is. And then we'll take 3, green, and cross off multiples of 3. And then it'll do 5 and cross off multiples of 5. And then it'll do the same thing with 7. And then it knows it's done at this point, and then it just identifies things that were not crossed off, and those are being highlighted in purple. And that gives you the prime numbers up to 120 in this example. So it's a very quick algorithm to find prime numbers, very, very useful. So yes, we do still use it today. In fact, both Euclid's algorithm and the sieve of Eratosthenes are algorithms that I study in my research from time to time. So, and you can, if you want to see this, I know if you have a slow afternoon and you want to watch the sieve of Eratosthenes on your phone or on your laptop, you can just go to Wikipedia and put in sieve of Eratosthenes and it will find this for you. So there you go. All right. Right. What's next? Well, sometime later, what is this, 2,000 years later, Charles Babbage. I want to talk about Charles for a bit. He lived in the 1800s and he built something called, well, it didn't get built. He designed it, the analytical engine. He designed it on paper. And there's a picture here of one of his engines. Is this the analytical engine itself? I'm not sure. But one of the things Charles Babbage built a lot of different calculating machines in the 1800s. He was a British mathematician, and this, of course, was well before electricity was common, and these machines were typically powered by steam engines. So the analytical engine was designed to have like a crank on it to do the calculations with gears and levers and things. And you can see some of those in the picture here, I believe. And the idea was it would be hooked up to a steam engine to power it. He built a lot of different calculating devices, and he got money from the British government to do this. One of the problems, well, he was grumpy, so people didn't necessarily enjoy working with him so much, but he's also brilliant, and he would start to build a new calculating machine, and as he was building it, he would get ideas for how to improve it and build a better one, and then he would give up on that one and start the new one. And the people who gave him money weren't real happy with this. And so by the time he had figured out how to build the analytical engine, which was a programmable computer, they were tired of him. And so he never got money to actually build the analytical engine. But the analytical engine was a programmable computer in the sense that you could write down instructions and sort of load them into the gear system of the machine, and then it would follow the steps of that program to calculate numbers for you. So it was truly a programmable computer. And they have since built actual copies of this machine. The London Science Museum has one, and I think they've got one that travels around like a traveling exhibit. If you're ever in London, I would encourage you to go to the London Science Museum and see the analytical engine there. They don't use a steam engine to power it. They have an electrical engine to do it. Yeah, so you're Ada Lovelace. You're ahead of me. let me finish with Charles, and then we'll go to Ada's the next slide here. I'll show you. There's Ada. Okay, let me finish with Charles, and then we'll go to Ada. Another thing that Charles Babbage did is he was a code breaker for the English military during the Crimean War. The Crimean War, I believe, involved France, Britain, Turkey, and Russia, and was fought in the Crimean Peninsula, which is near it's right next to modern day Ukraine, or some might say it is a part of Ukraine. I'm not going to, go down that road, but it's an area that is currently dangerous to live. But the Crimean Peninsula is in the Black Sea, and there was a war there back in like the 1850s, I believe, 40s or 50s, and Charles Babbage figured out how to break codes, and so he got quite the nice reputation as a result of that. So yes, all right. So there I have if you've ever heard of the Charge of the Light Brigade, a famous poem, that happened during the Crimean War. Just because you break enemy codes and know what the enemy is doing doesn't necessarily mean that the generals do the right thing in response. And I think the Charge of the Light Brigade was an example of miscommunication. It did not go well for the British, but that was all part of that war. So there you go. We have a deep question here. Do you think we would be anywhere near as advanced as we are now if war hadn't forced advancement? Yeah, that's a really good question, isn't it? War does seem to spark innovation. There's a lot to do with that. Yep. So, yeah, we could probably spend a half an hour just talking about that particular question. But yeah, it seems the case that war sparks innovation, and a lot of code breaking was invented as a result of war. And as we'll see a little bit later, other things as well. So, all right, I promised Ada Lovelace. So let's talk about Ada. So she lived at the same time as Babbage. She had poor health and did not live very long, as you can see here. But she is credited as being the first programmer. So Ada Lovelace, she was the daughter of Lord Byron. You may have heard of him. He was known for his writing and adventures. But she was trained as a mathematician. Now, at this time in England, women couldn't go to the university to learn. So she learned from tutors and friends and things like this. And she worked with Babbage. So given the perhaps given the definite unfair situation for women at the time, Ada was not able to be picky about who her instructors were. So she worked with Babbage. He was happy to work with her. At least this is my understanding. And so the two of them did collaborate quite a lot. And she ended up publishing papers that contained programs for how to program Babbage's analytical engine, which was not built in her lifetime, but she wrote programs for that. And so we call her the first programmer as a result. And the very first program she wrote computed something called Bernoulli numbers. I'm not going to try to tell you what those are, but you can certainly Google those and learn about them. They're very important in applied mathematics. So that's something that she did. And we celebrate Ada Lovelace Day every year. This year it's October 14th, 2025. It's usually a day in the first half of October. We celebrate Ada Lovelace. So she is certainly noteworthy. All right. The next person I'd like to speak about to you is Alan Turing. Alan Turing lived a little bit later, early 1900s, from 1912 to 1954, and he also did code breaking during a war. There's a lot that Alan got done in his short lifetime. So we consider him the father of theoretical computer science. He was working on something called the Entscheidungsproblem, which is just German for decision problem. It was a problem in mathematical logic. And in the 1930s, he came up with a solution and invented theoretical computer science as a side effect of his proof. And that included the concept of the operating system, the idea that you can write a program that runs other programs, and the corresponding idea that programs can be treated as data. So the whole idea that algorithms are data is something that came out of Turing's work. So this is part of his theoretical work, and that happened before World War II. During World War II, he worked at a place called Bletchley Park and helped the Allies break the German Enigma cipher. And you may, if you're familiar with geography a little bit, he worked for England. England fought against Nazi Germany during World War II. Britain is an island, right? So everything they needed to fight the war, feed their people, had to come by boat. And Germany had this fleet of U-boats that, basically submarines that they had created to try to basically starve Britain and get them to surrender. And if you didn't know where the U-boats were, they would find the convoys and sink all the supplies and kill the people, and it would made things tough for Britain. So breaking the code to figure out where the U-boats were so that you could send your convoys of ships around the U-boats was absolutely vital. There was no way to get American troops, once they entered the war, to England to do like the invasion at D-Day unless you could get them across the Atlantic. And you couldn't get them across the Atlantic if the U-boats were sinking everything. So breaking the code was a precursor to, absolute necessary precursor to something like D-Day that helped, defeat Germany during World War II. So it was very, very important that this happened. And his work was central to that. So let's see. I'm seeing the questions move around, but I think I've caught them all so far. All right. After the war, so the war was over in 1945. After the war, Alan Turing worked at a national lab and helped build one of the first computers in the 1940s. The one that he worked on was called the Pilot Ace computer. There were others that were built at this time as well. But basically, if you think about it, computers were theoretical, not physical objects before the war started. But through the war, they learned that building automatic computation devices was necessary to break Enigma, because Enigma was a machine and you needed a machine to break a machine. And so World War II helped bring the beginning of the computer era. And right after World War II, suddenly we started building computers. So this is a direct consequence of World War II. Alan Turing also started research into artificial intelligence. He wrote a paper in 1950 that talked about the definition of intelligence when it applies to artificial intelligence programs. Out of that came what we call the Turing test. And we use reverse Turing tests all the time for people to prove themselves human, CAPTCHAs, basically. You probably do get to play these little games now and then, like finding the motorcycles or typing in the letters and numbers. That's all reverse Turing tests that we use today. So that's all due to Alan Turing. So Alan Turing did all that work. Alan Turing was homosexual at a time when it was illegal to be homosexual in England. And basically he was persecuted for this. He was given the choice of take injections or go to prison. He chose injections. It's believed that led to his depression and eventual suicide in 1954. So that is what happened to Alan Turing. And if you're curious to learn more, I can recommend the movie The Imitation Game. It is not completely accurate in all the events it portrays, but it's roughly accurate. And it certainly captures the feeling of the time. So it's a very good movie. I would recommend that to you if you've not had a chance to see it. All right, I think I've got a picture. Yeah, so I've got a picture here of the machine. It's called the Bomb on the left. All those little rotor things you see there are duplicates of the rotors used in the Enigma machine, used to try different key combinations. And they built, by the end of the war, they had built hundreds of these machines to break codes. Those were used extensively during World War II. And then the picture above on the right is a picture of the Pilot Ace computer. And you can see, some of the wiring and so forth. And there we go. And of course, the cookie pictures, it made sense to have cookies that hide other cookies. So I've never tried one of these, but I'm curious to. A chocolate chip cookie that has an Oreo cookie on the inside. So Yeah, that looks pretty yummy. So anyway, so yeah, we started building machines to break codes during World War II, and suddenly we had computers. So the earlier question about, yeah, does wartime spur advancement? Well, it certainly seems that World War II brought about the computer revolution, or at least maybe made it earlier than it would have been otherwise. Why is it called the bomb? I think because as it worked, it had a ticking noise, probably, and it was a joke. I mean, one of those dark humor things during war, right? That's my guess. I think you could probably Google that and find out for sure. So if you put bomb, put the E on the end, communications with the words like bombs and so forth in it is not a good idea. So put the E on the end there. Any other questions before we move on? Looking, we've still got what, 10 minutes. Yeah, we'll be fine. The next person I want to mention is Grace Brewster Murray Hopper, or Grace Hopper. She was around in the 1900s, and she had a PhD in mathematics from Yale. She was in the Navy, a rear admiral, and she worked on early computers like the UNIVAC, the Mark I and the Mark II. She invented the COBOL programming language and other things. One of the things, interestingly enough, is that her team is credited with finding the first computer bug. The bug was a literal moth found inside the wiring of the computer, and the log sheet for that day is in the Computer Museum, I believe, in Boston. And here is a picture of it. There's a picture of the moth under a piece of tape, and it says right there, you know, first actual example of a bug being found. So that's kind of amusing. So yeah, early bugs sometimes were actual insects inside the wiring of the computer. And we have there's a website that celebrates. There's like an annual conference for Grace Hopper that encourages technology and computing for women. So that's something to look up if you're interested in that. In the 1970s, there was this company called Xerox. You may have heard of Xerox. They had they were well known for photocopiers. They had a research group at the Palo Alto Research Center. That's where PARC comes from. And at that research center in the 1970s, they had a team that invented some things that are kind of important. Object-oriented programming, Windows, the idea of having a window on the screen to represent what's going on in the computer, and the mouse, and the idea of clicking and dragging things. And you can see here a picture of an early, window with objects on it that the mouse could be used to select and drag around. This was built in the 70s. There was a team from a small new company called Apple Computer that visited Xerox PARC and saw these ideas. And they ended up taking those ideas and creating something called the Mac computer. And there's a picture of an early Mac here, and you can see it has a mouse and a screen with objects on it. So that was nice for Apple Computer to take those ideas. Xerox knew they had these ideas, and in its infinite wisdom, the board running Xerox thought, no, that computer stuff, it's just a fad. We'll stick with what we know makes money, making photocopy machines. So missed opportunity there for the Xerox company. Little irony. But how big was the window? Screens, if you just imagine a television screen, the screens were reasonable size. It's just they were black and white. We didn't have, the same stuff we've got now back in the 70s. Smaller, was it bigger or smaller? We had cathode ray tube screens back in the 70s. So you didn't have flat screens. So they were big and clunky. Yep. That was what they were like. All right, let's talk a little bit about artificial intelligence. We've got, 5 minutes left, so we've got a couple more slides to get through. IBM designed a system called Deep Blue to play chess. And you can see the picture on the left shows the Deep Blue machine. And in 1996, for the very first time, the Deep Blue program beat the world chess champion at the time, Garry Kasparov. And that algorithm that it used looked ahead 6 to 7 moves typically, but on occasion, when the situation merited, it would go as far as 20 moves look ahead. So that was the state of artificial intelligence in 1996. And then moving ahead, In 2011, IBM came out with a program called Watson, and it's much bigger. So on the screen here, I'm assuming you're familiar with the Jeopardy game show. Watson played against two very well-known Jeopardy champions, one of whom, Ken Jennings on the left here, is currently the host of the show. But Watson trounced them, as you can see by the scores here. And it used a more Google-like text search algorithm to look for answers to questions. And it had racks of machines, probably dozens of racks of machines to achieve this level of competition. But that's advancing in AI in the context of game playing, which I imagine many of you have some experience with, playing games against artificial intelligences of some form or other. Then the next step, the game of Go. I don't know if you're familiar with Go, where you place either black, you're either black or white, and you place stones on intersections of these lines on a square board, and you can capture pieces of the other side. It's a more abstract game in terms of strategy than something like chess. It's harder to do lots of look ahead because you have so many possible moves. Google's AlphaGo program used machine learning, and the program learned how to play by playing simulated games against itself to evolve its strategy. The game's strategy to play is not understood by the people who wrote the code that the program uses. Get your mind around that. So the people who wrote the program that AlphaGo uses to train itself don't understand how AlphaGo chooses its moves. And it back in 2016, it was defeating the top Go players from around the world. So it had succeeded there. So that's AI has advanced a great deal, and that's like 9 years ago now. So AI has come a long way, a long, long way. It had a long way to go. So what's happening in the future? Like what's going on now, what's going on in the future? I'll just mention a few things we see on the horizon here. Neuralink is the idea of building devices that interact with your brain directly instead of using, awkward screens and keyboards and mice and things. Let's just wire you right into your brain. So there are several recent companies. I think one of Elon Musk's companies is working on this technology as well. So I don't know, would you put one of those things in your brain? I'm not sure, but that's something that's going on. Virtual reality has become a big deal, and that's going to improve. So quantum computers, we've been building quantum computers for several years now. They're not quite big enough to take over, but they are getting better and better, and there's a lot that they can do. Well, they can't do anything that current computers can't. There's not more that they can do. They just do it so much faster that it makes them a huge improvement. But they're very difficult to work with. Self-driving cars are coming. Do we have AI good enough to navigate a car? I have an uncle who's not good enough to navigate a car, but I guess that's a different question. But yeah, do we trust AI to drive cars? And they're not perfect. I think we've got some learning to do, but I just saw an article saying that Waymo was going to expand to like Las Vegas and several other cities for driving taxis, self-driving taxis, that sort of thing. Generative AI has been a big deal the last couple of years. That's been taking over industry and commerce and so forth. I think the hype is bigger than the reality, but the reality is there's something there going on. So that's kind of interesting. And then this notion of the singularity, if you've not heard of it before, the idea that AI can improve itself and get better and better, and at some point surpass what humans can do with their brains. Will that ever happen? I don't know. We'll see. We'll find out. I got 1 minute left. Do we have any last minute questions? Well, thank you for your attention. I hope you enjoyed it. I hope you have a lovely day here today, and feel free to reach out if you have questions. You can Google me and get my email address, or it's probably attached somewhere in the conference here. So feel free to reach out, and it's been a pleasure. Have a great day.